Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our practical lecture 4.1 about MPI communicators and a little bit about data structures in MPI. So that basically builds on the MPI lectures we had before, especially the one that we have in lecture 4, which was a bit abstract with all the communicators we had, especially the Cartesian. So we will have some examples around this, and also we'll demonstrate a bit about non-blocking communication. Then the second part of this lecture will be more about data structures, MPI-derived data structures that we can create. But before we start into the material in practical lecture 4.1, let us review what we had the last time. So in the advanced MPI techniques, we really go, as the material suggested, advanced. So we had MPI with broadcast and the collectives in lecture 2. We had also there send and receive messages, which were all, let's say, blocking communication. Hence, the application logic was not continuing. But in lecture 4, we basically, in order to do more sophisticated MPI applications, we took lecture 3 into account about domain decomposition and then several other elements of it and connected it nicely to lecture 2 to really show a little bit more what is capable in MPI. And this should really show you that firstly, MPI is very rich. It has not only blocking communication, as we learned last time, also non-blocking communication. That is a bit illustrated here. We know from the first lectures, we have MPI send, and there should be an MPI matching receive from another task. And this is something which could also allude to performance problems. For example, here you see a sort of late sender waiting time, right? Which this process is already very long in the MPI receive command while it waits for the late sender here to do something. But then to basically show an example how it also can work with non-blocking communication, and we will have some examples here directly and indirectly today when we talk about the Cartesian communicator. There are also other ways of doing it. For instance, you have here this MPI send, and then you have this, basically non-blocking communication I receive. And then in order to have some barriers and to some synchronization of all of these different tasks at different methods we learned the last time. One of it was MPI wait or wait all, or also even the barrier we learned. Hence, when you start into this non-blocking communication, we will find a situation where the application logic gets a little bit more harder to follow, because in the end, it gives you the benefit that, as the name suggests, we not block the communication, and we can do some other things while we essentially wait for the send here. But on the other hand, it also shows that the application logic becomes a bit more complex than just having a send and receive. Like, for instance, introducing the synchronization that I'm talking about. And we will have some demonstrations, so I think that becomes then very clear through these demonstrations. Another big part related to communication in the last lecture was also then the communicators again. We had that a couple of times, so by now you all know that MPI world is the world of all the processes that we have in the MPI environment. Here it's 10, 0 to 9, and I can split them in different groups. And how I split them is really something which depends now on your application logic. You could do what we learned the last time, so a simple group of saying I have 16. Let's maybe just split them equally in groups of 4 with the MPI split command. And then you have created so-called subgroups. And it's important to realize that then basically you usually get a new rank for it, right? While the original rank that you have in MPI world will always stay the same, in the new communicator, you have usually another numbering of these ranks. This is important. Then we also learned one more, let's say, advanced Cartesian communicator. We, from the logical perspective, already introduced that a couple of lectures already when we said about domain decomposition, chopping up the domain in equal blocks, and then we came to the idea that it looks pretty much Cartesian. But we also learned, and then a lecture for the beauty of MPI, really, of saying, I didn't need to know any of the low-level networking details, right? That is very nice. especially if I think about that I have a neighboring setup and how in the world I should know my neighbors, right? I have, let's say, 12 processes, or better to say in the job script, I say 12 tasks. But how in the world should I know who are my neighbors when I want to send and receive messages to them? For instance, like physical variables, you want to transport them over the domain. You can think about the fishing simulation. We already had a couple of examples where you want to have the fish population swim maybe in this direction, at some point also maybe periodic, so coming again at the top of the simulation. But this is something where I have to send and receive messages. As you know, you have to have someone already listening or also someone sending, and these ranks need to match. And the beauty of this Cartesian communicator gives you exactly this. So you can do a shift and you get basically the information that you need in order to perform a send and receive. Hence, what I said also the last time, shift is not doing anything. It just gives you the ranks that you can use then for send and receives. That's often done wrongly by students or wrongly understood. The shift is basically just the idea of how to perform or prepare better, basically, the communication. Then the actual way how you transport data will be still, as we learned, some message exchanges with send and receive, for example. However, we also learned one of the things that is affecting the communication very much, and this is the underlying network topology, the underlying setup in the HPC system. Although MPI gives us a very nice abstraction here, and you could think of much bigger grids, of much better and bolder simulations, as we heard, especially towards weak scaling, right, and increasing the performance, granularity, more and more tasks per core, more and more activity really and processing per core. But then sometimes it's really limited in the execution that we have in the hardware level. And one example was, for instance, in systems where there are dedicated I/O nodes. So when you do, let's say, I/O and you want to drop elements to disk, basically the message exchanges that you have here with the red line are already affecting all your interconnectivity of all the different cores and nodes. And hence the performance of this is something what you have to observe with performance analysis programs. And we have also learned about different topologies with the fat tree, oversubscribed connections, where you have essentially the idea of lots of compute nodes and you have this file service, but in between, you have an example here, is of course a little bit the bottleneck with the InfiniBand systems of having the switches in between. And we learned as the communication is very expensive in terms of really having the lines there. So talking about, for instance, InfiniBand with a all-to-all connection to all the different nodes, because that's maybe what you want to do in the MPI application. We see that this is a very cost-intensive factor together with accelerators today. But in this sense, the idea of more modern network topologies go to so-called this dragonfly topologies that you have seen, and some regional cells and so on. But that's not so important. More important is maybe to understand the parallel and scalable I/O methods we had the last time. I think that's also important for you to understand that not everything is computation, not everything is communication. In one respect, also the application performance and really making it high performance is also relating to data. And that's a view we didn't have in the course so far. And we also intensify this today with some other ideas how you can use MPI. This was just a broad sense of saying we have this, all the memory data that we want to basically in some point in time dump to disks. It doesn't matter if it's distributed memory, shared memory, whatever. And in this sense, we have different options. And we learned that, of course, you could have this master worker paradigm of saying here, the process 5 is collecting all the information as a master and then dropping everything to disk. However, this, of course, is also prone to load imbalance and also overcommitting the master, especially if you now consider that you not only have 5 processes here, but very many. So a better way in one respect would be then thinking about why not every process is doing that on its own, right? You would quickly come to an idea. You have a sort of message exchanges here in the application. And then at some point in time, it's time to dump things to disk, maybe checkpointing, And then, everybody writes just a simple file on its own in the file system. So the disk would look like this, right? You have a disk with many, many, many files. And now think about, again, not this 5 that you have with 5 processes, think about now thousands. And then quickly we come to the point that here the file system has really challenges. All of them needs to create inodes, update inodes about all of these files. And this can quickly also become not a high performance solution. So what brings us then to this real idea of parallel and scalable I/O is then the idea that we have a so-called logical file, which we can write in all together. So enabling a concurrent access to file from all these processes, writing in one big file if you want. And this is this parallel I/O we talked about the last time, which is specifically good supported in parallel file systems, which have then this 2 times mapping. So you would have different threads or tasks that actually enter the file, this logical file with file pointers right into the file, often also in a binary way. So we have talked about HDF5, for instance, a file format on top that we will review very quickly today, but also then learned, of course, underneath, we still have different I/O nodes with different storages underneath, where we then do some different storage elements to fill. Although this file looks as a one big logical file, it could be different physical blocks basically underneath. And this concludes a little bit the overview that we have in lecture 4. Many of these concepts we have learned the last time. I will now demonstrate a little bit, especially the communicators, as they are also relevant for one final project in the course, for instance, a Cartesian. So let's then go ahead, look a little bit how we can see the advanced MPI techniques now in some real practical examples on ELIA. Hence, we will have a blocking non-communication here. And this is, of course, wrong. We don't have Newton anymore. We have now the ELIA system. Sorry for this. Basically, here we will do this non-blocking and blocking communication. And we have the weight function that we will demonstrate. And then we really come to the Cartesian communicator, thinking about the dimensions that should fit your job scripts. We have to understand the shifts and some different configuration parameters really that you can use with a Cartesian communicator, like periodic or reorder and so on. Using this in some simple application examples, just for you to demonstrate the neighboring mostly really of the Cartesian, will be then part of this particular example. Then when we think about the MPI derived data types is something what I wanted to show you as one of the options how you can work more advanced as MPI. We didn't cover that much in lecture 4. We put there an emphasis on the parallel I/O in generally to understand this. So the MPI derived data types is really an idea to further work in MPI with more advanced data types. And I will make the case for it, why is it useful, and give you some couple of examples. And then also think about the data science example we have in HDV-Scan. We can also look a little bit in this, see and understand the parallel I/O binary file format that you basically can here see on the slides. I cannot demonstrate that very much because it's not installed on ELIA in the moment. So that's a problem for us. We cannot, sorry for that, also demonstrate that right now. But at least the slides give you an idea how that works. So let's come back to this learning outcomes. We do really, again, many different aspects of parallel programming. For instance, scheduling will come again. Also to think about that we're now getting a bit more in the number of tasks, maybe 12, maybe 16, depending on the Cartesian grid, for example. Then the HPC environment tools that support the programming are important. So we look more on the S control again, show job IDs, the scheduling parts, of course, but also thinking about that, this MPI with the Cartesian is a perfect foundation to really work with scientific domain specific applications. So it's really a practical lecture again, with having different tools where you can go into parallel programming right off this lecture. Let's start a little bit with blocking versus non-blocking communication. And in my review of lecture 4, I already had pointed out many points of it. So here I will be very quicker. I mean, much more thinking about a demonstration. So let's go and go into this concept of non-blocking communication. So here I'm already logged into our alias system. So you see we are on the login node as we should be. We have different controls there. Who am I? Morris. And we see now that we have our old HPC course setup. What is new now in our MPI lecture is that I have some example here for non-blocking. So let's move into this. In order to understand this, we have a non-block example C program is here prepared, which showed us a little bit how that works. We have a usual init of the MPI environment. We get the size of all the processes that we get. We get the rank from my own. And essentially we already understand that we have a process logic apparently for two different roles. Because here I have my rank equals 0 and I have my rank equals 1. And what we want to demonstrate is a little bit this sort of, I did already something with send, but I still can, print something out. So I do something, right? So we see that a little bit here. When I say, if I rank when I'm basically rank 0, here I have a couple of things I want to write out. I can get some processor name, CPU name, and so on. So essentially this gives us a node information, and we have here a couple of variables defined to send something and also get the CPU name field then, which is then the idea of the whole application. As you see, firstly, we have someone who is then sending something, which is this non-blocking send. And this send buffer is something we want to talk about then and, send this over the line, but have, of course, some receiving one on the other hand that is then starting with the other part here. So we have to move a bit down to be ready, of course, to receive with the non-blocking receive. So hence, here we already look both roles, right? So I think firstly, it's understand that we have this application logic, which is split in two, and one takes the non-blocking send, and the other one the non-blocking receive. And this is something which is important for us. So here we say we have a receive buffer, and when I do this, the interesting thing is between the wait, which is then waiting on this particular request that I have here put into this iReceive command. This is now important. This needs to match, and we get a status information out of this, what really was happening. Hence, we assume something like that this application logic will split. One of the processors will say, or one of the tasks will directly go into this iReceive and not wait here. That's now the counterexample to the typical receive. Hence, it will directly print out, I've just started this receive and I'm having a good time relaxing. So nothing happens, right? And it's waiting then, but at least it could do here some work, although it is still waiting for the receive, which is now the interesting part. But we see with MPI wait, we synchronize here and don't go further. Why we don't go further is because we have rank 0 doing at some point in time, and this is again the interesting thing. We first say, we basically go here in this particular element, send something out, and then we'll use this isend command to actually get something over the wire, which fits then here this non-blocking receive on the other hand. Also to demonstrate mostly this non-blocking toy example here, we see that it will run here in the non-blocking send, but also, right, also that you show and see that between the send and the wait, which is then also here, of course, now waiting if the send was really received. This is something where we then synchronize. Hence, it's a sort of ping example, right? There's not really a POM because they don't send something back, but we print it out to really let you know what's happening. So, good. The last point is really using this request information. where we can get some information out. If the request was null, then that means it was really successful, the request was running, and it's not still, let's say, around, so that we know, okay, of course, with the MPI request, we also wait for this. So in a way, it's clear that this is coming out and this should be the outcome. So in a way, a very theoretical view on the source code, which I can talk more long about it, but let's go into some practice. Firstly, we want to have this module load examples. Again, as you know, we can search a bit in the history, so let's make that a bit easier for us, which having the module load here with the module load MPI OpenMPI version. And then I have this MPI CC non-block example.c. As you know, with the O, I always want to have this a little bit more streamlined with a name. And there will be some warnings, which is there, but essentially you can see that the executable is created. And with this, we can actually use the non-block example. There are several warnings and so on where we have to see a little bit. For a perfect example, we have to have much more source code. And as I said, the software engineering part that you see with all the warnings here and so on is something where we not really have to go too deeply into it, because we essentially just here want to show now that we have this non-blocking communication. Hence, the parallel computing aspect is now the most important thing we want to show, not how you perfectly program it and so on and so on. So having this executable now created, let us now think about how we SBatch it. And for this SBatch, we want to have the submit non-block example looked at. Our job script, now what we do is we have a non-block example on the partition utun. We just have two tasks per node here. And then, as we know, we already have to also load the modules for it to get the non-block example running. So we SBatch this, submit non-block example. We get the job ID here. We do the S control, show job ID -dd for more output on this particular one. And then we see, okay, it's really already completed, which is nice, but also shows that we have two CPUs used here, and we have been running on the compute one node. No surprises for you. Given the job ID, we also assume some output here, which is then this one particularly with the 82 at the end. And what we see is now this conversation we sort of a little bit expected from the source code. Here, hello there, user, I've just started this receive, etc., etc. We see also the node information coming through that we requested, which is another idea of the MPI. Now, what I wanted to show you, it has a bit self-awareness where the rungs are running. You can get this information as well too. It could be different nodes. And you see also the MPI request is null now. And then the other conversation part, when we take now the other role, is that dear task one, please don't send any more messages, send money instead, etc., etc. Task 0 and running on compute 1. And also here we see then again the MPI request null. So that was running, and it shows you the text was giving out, and it still continues to work with the MPI wait. Of course, this is a toy example. In larger setups, this is much more something to consider with weights and barriers and elements for waiting, maybe wait all. And some of this is indirectly also in our Cartesian examples I want to show you next. But of course, the elements I demonstrated to you here, and these are things we already discussed in lecture 4, so I skipped that a little bit. This is the same elements we had already discussed there that were also in the review of the last lecture. So the source code I just presented you is also described here as I just explained it in the source code itself. So something like this, where for some of you that want to go back and want to understand it more in detail, perhaps you have all the description I just talked to you also in the slides. But let us go ahead to more interesting examples. You know also by now how to actually here compile it, how you load the modules, the right ones, and so on. So it's also not a big, let's say, surprise, and how to actually then submit it with these two task per node. We have seen also the outcome here. So this is all what I just presented. Now let's move ahead to the Cartesian communicator, much more complicated material, but also this we had now quite a lot in lecture 4. Also here, for the sake of the practical lecture, I would keep the explanation of the Cartesian communicator now to a little bit the practical setup. Let's say we want to create something like this, a conceptual view. We have a 3x4 grid, and I want to demonstrate you a little bit how we create such a communicator and how then we also come to this periodic behavior. And most notably also where you get your neighbors, right? So we want to have something like here where we know, okay, my destination, when I want to send something from this particular 0 processor, then my destination would be 4. So I need to get something out that my neighbor below would be 4. But I also want to get something out that my source from which I get something when I do a receive operation should be 8, right? Because this is the Cartesian structure where I should get information from, but sending to 4. And that is the same for all the different Cartesian grids. Hence, we get a complete awareness where we're running, what rank I am, but also sort of what row and column I play in this bigger picture as a rank. And with this, I'm also able to get the source and destination. So let's go into the example. I brought you here a Cartesian example, which is also, of course, documented on the slides. But as this is a practical lecture, let's move a little bit into this. It's a first small toy example of this, where we have here, of course, the usual MPI environment. We're going to create, we have the dimension I just talked about, the 3x4. We say it's periodic behavior. And a couple of elements that we also have to put in, because that's what we want to know, the source and destination, for example. And then an MPI communicator that we have here as a variable that we then have to create out of MPI com world with the dimensions we just described, with the periodic behavior, reorder of the ranks, and then putting that in the variable com2d that we defined here. Hence, from this one, when we created this, we have suddenly a new communicator. As you see here, when you get my Cartesian coordinates to understand in which coordinate I am filing, I don't anymore think about MPI com world. I'm now in the world of this 2D communicator. I still have my rank information, which of course helps also the MPI information environment to understand where you are. And then I said to you, we can do a shift, which means it fills the source and destination information, but it doesn't do anything, right? It just fills the variable source and destination. When you really want to send something, what we do, we reuse this destination information here with a send and receive in one operation together, a new command as well for you in a way. So where we have also the source and then sending this all in the communication to the communicator. Get a status out. And we use then, of course, all of this information we just obtained with the source and destination to give a little bit out. And this should be something where we then get also the coordinates and a little bit information about each of the ranks. Now think about, we have a 3x4 grid, and the key element of this example is we need now a job script that is fitting to this 3x4 setup. Hence, we assume that this here should be 12 times executed. Right? Hence the 3x4 grid. The same source code, really much the same as you see here, should be 12 times executed. But given the Cartesian and the different ranks that I got, this output should be very different. I mean, very different in the sense of the variables that will be filled differently, 12 times. So let's see a little bit how that works when we go into the submit card example. Job script, also here, no surprises, but important for us is 12 here. So 3x4 equals 12. So it should be matching to the Cartesian. And then I will run my MPI card example. Again, let's help again with the module load command here, which you by now basically don't have to do because we already loaded it. Just for the sake of completeness, we do MPI CC, essentially with the card example.c. We -o it with card example, and then we'll compile it. It worked. This time no big warnings. And then we can really batch this example, submit card example, and as control it, show job ID It's probably already finished, but I want to show you then that we have also really used this 12 cores here in this example. You see the number of CPUs is 12. We remain in one node compute 1 because it has enough capacity for it. We also see it's a very small job, so it's already completed. As many of the examples I present to you, of course, this is different from many different physics applications that are much more larger. We also see an output here. We see the 87 that we had here just in the output, and I think no surprise, as you can imagine, we have this 12 times because we executed source code 12 times. Think about the rank information, of course, is 0 to 11. Hence, it was working, and we can nicely see now the kind of same element we would have in the slides when we had, for instance, rank 0. We remembered that the source was 8, which was in this grid here. The source was 8, where I get something from in this periodic behavior. And I know also here in the destination, it is 4. So that means I know as ring 0, when I want to send something to my neighbors down, it is 4. The direction is often a question that was in the source code. It is actually part of it and also well documented here, where we obtain process coordinates in the Cartesian topology, depending now on the shift in which direction we basically go. And here we have this step where we go below. So essentially to match what we see on the right-hand side, right? And then we gave it out, we send and receive elements. If that would be not the case, you can imagine that we had here the information about these different ranks and so on. Yeah, and that's really important to understand the Cartesian coordinator. I think I don't need to go more in detail. As I said to you, as usual, everything is documented on the slides. Which more information, maybe a little bit about the periodicity, where you can also have this basically here as a kind of a part in this Cartesian create, right? So we said periodic, okay, and then reorder, and then the periodics is something where we have here a kind of configuration parameter that we can do. And with this, you can have different setups. You can imagine we want to maybe have a periodic behavior of saying up and down, and should be starting again, let's say fish swimming all the time or from left to right, but maybe you want to do actually also both. This is a very simple configuration parameter, and the MPI coordination or the MPI card chords is the one that you get all the information from for source destination. Then the shift that we discussed is very important, doesn't do anything. As I said, also important, of course, for the Cartesian shifts is there's lots of different ways how you can work with it. And also some things which you have to think about. I mean, firstly, of course, you can go in different directions. It's very clear. But if you don't have periodic, so to speak, then you could be also coming to the end of the Cartesian. That is something, of course, you should have in your mind when you maybe have a placement. So you go in the non-periodic one that you defined, and then you can imagine if you always continue with a kind of, shift, so to speak, you ending somehow in MPI proc null, meaning you're at the end at the Cartesian. When you do this with a periodic setup, this problem is basically not existing because you will be then going to the turnaround, so to speak, that we have discussed. And that's what really was also in the in the part. Here's again the example where I said if B is like here B is 100. So if we would not get the information into B here for the output that we later give out here is B again, you can imagine that essentially we would have a problem here. So everything was 100, but as it was working, we never saw 100. That is also not the case. We have run it. That was beautiful because I have 12 tasks, but I wanted to show you practically also a little bit of situation which you should avoid, which is then, of course, going to the card example. Also, this is documented on the slides, no worries. But let's put 11, right? 3 times 4 is 12. So we assume when we execute, for instance, this with 11 tasks, it will be not enough, right? And we can see here as control show job ID minus DD, and then come to this particular example, failed, right? So that's now not nice for us. We have 11 CPUs, but you can imagine the problem is it doesn't match the Cartesian communicator. Hence your output would be here, where you see essentially that the MPI card create couldn't really create the MPI environment as we asked for in the source code. Hence the dimension doesn't fit, which is not good. And hence we add this quickly back to 12 to in the next time also be able to run it again. This is also documented on the slide, a small takeaway message here. When you have 11, obviously that's not matching the dimensions that you have in your C code. The output we checked, so this is now again the idea that we have seen. Let's, however, come to a bigger one where we sort of combine now non-blocking communication with Cartesian communicators, and which is really going towards a production setup where you have 4x4 setup. Let's say 4 neighbors, you want to exchange information, not only do a shift and do, you know, communication in one direction. Now let's see how a source code would look like if I have maybe a Cartesian grid of 4x4 and I want to exchange this for all my neighbors. So here would have an in buffer created, then your neighbors, which should be 4, the dimensions 4x4, as we said, to make it 16. We have a helper variable here, size 16, but also define up, down, left, right with different numbers. We have the reorder, the periodics that you already know, and the card com that will be now our communicator. So because it's a practical lecture, again, I will go less on slides, but rather a real working example so to get a message that this is also indeed working. Now let's go to this and look very briefly in the C code. Many of the things I just already created, it's very similar with the Cartesian creator that we just said, and also with the idea of, so here we create, of course, this Cartesian communicator out of COM_world, and just then of course use these information before to get the ranks coordinates in this new communicator. But then also I want to prepare shifts depending on our neighbors to the left and right and up and down. And so with this being able then to really getting out information in all the different directions and saying then for us, which is now important, what neighbors I have, you know, up, down, left, and right when I now do this information. And this is important for us. If you think about that, of course, now I have 4 neighbors. I have to do a send and receive to all of these different ones. In a practical performance, I mean, in a practical application example, where we then get some information, physical variables normally. Here we, of course, exchange the information of the neighborhood information. So it's also more or less a toy example. Important for us is also I do this in a non-blocking way. Hence, we need a synchronization at the end of all of these different requests that we have here that we execute 4 times now. That's important. All my 4 neighbors, as I discussed, and going with the E here through it. And this could be really extended to much more important thing, like for instance, in some respect, some fishes swimming, maybe to the also parts, which is one part of the final project. But yeah, let's come to an example now when we think about the job script quickly, where we have the submit card 2D. Also here, no big surprises how that looks like. The only real big difference is here the 16. I have a 4x4 grid, hence the 16 should match. I S-batch it, this Cartesian 2D example, and then can see in this command really that firstly, I hope it's completed already. It's a very small job, as you already know. And as we were requesting, we got 16 CPUs for these tasks. For the output perspective, because the job is already completed, we expect now that we get neighbor information 4 times for each of the different neighbors that you see here. Rank 0 has, you know, the neighbors 12, 4, 3, and 1. Now on up, left, and right, and so on. And then also we see it has received then also this information from these neighbors, as our source code is alluding to. We have the ranks from 0 to 15, and this was all working. We have the output here, and shows you essentially now that every of the rank has the full power to understand in which context it is to really do send and receive messages to all the 4 neighbors. And this is often used in the physical applications and simulations and so on. And with this, I go quickly back to the slides, but I think by now you can understand that many of the things I just described here in the source code is already on the slides. So no need to repeat this. For loop is important to have really the send and receive really working. As I said, the shifts that you see here, preparing it, but then the I send and I receive really doing it. And this is important. We have the synchronization with wait all, which is also important to understand. Then here we also wait for all the requests to finish. Also toy example, still it already captures a little bit the essence how that would work for one time step. Now, if you want to have a time step of a fishing simulation over time, let's say 20 seconds, you maybe would have a for loop around that as well again, right? Or a loop more generally catching then these time steps. And in each of the time steps, you would do this communication, exchange variables, and then do your other physical part, let's say calculate the wave height. Then in the next step, you would then also show a little bit the neighbors, how the waves have been propagated over the tiles, or how the fish was swimming over the tiles. There could be many different application examples. And in a way, that's really the main message I wanted to bring in the first part. So we have finished this, and I will go in the second part a little bit more into MPI in terms of derived data types. We'll demonstrate this. However, we didn't manage to have this HDF example ready to demonstrate this year because we were switching from Utin to Elia, and we didn't install it on Elia yet. However, I have some slides where you can see how it looks like with a binary file format. So see you in a while.